Welcome to Manasi Solutions. Let R be a commutative ring with a unity and let A be an ideal of R. Then we are going to prove that the factor ring R over A is a field if and only if A is a maximal ideal. So if we proved this result, then we can say that if A is maximal, then R over A is a field, and if R over A is a field, then A will be maximal ideal. Now we are assuming R over A is a field. R over A is a field, and we need to prove that A is a maximal ideal. To prove this, we know that an ideal A is maximal if there does not exist a ideal B such that A properly contained in B and B is properly contained in R. If there does not exist such a B, then we can say that A is maximal ideal. And to prove this, first let there exist an ideal B in R such that A is properly contained in B. A is properly contained in B. And we will prove that B equal to R. So A will be a maximal ideal. And since A is properly contained in B, there exists an element in B. There exists an element in B such that B does not belongs to A. And consider the element B plus A in R over A. Here B does not belongs to A, therefore B plus A is a non-zero element in R over A, and R over A is a field, therefore B plus A will be a unit in R over A. In a field, an element in a ring, an element is said to be a unit if it has a multiplicative inverse. So here B plus A is a unit, therefore it has a multiplicative inverse in R over A. So there exists an element C plus A in R over A such that B plus A into C plus A is equal to what? 1 plus A. This is the multiplicative identity, which means unity in R over A. Now look at the left hand side. Here B plus A into C plus A is equal to BC plus A, and which is equal to what? 1 plus A. We know that if A plus A is equal to B plus A, then A minus B, then B minus A belongs to A. So by using this result, we can say that 1 minus BC belongs to A. So, and here A is contained in B. Therefore, 1 minus BC belongs to B. And now, here B is an element in B and B is an ideal. And by definition of an ideal, we know that for any A in an ideal A and for any element X in the ring R, AX will be in what? A. So by using this statement, we can say that here B belongs to B and C is an element in ring. So BC belongs to B. Now look at here, 1 minus BC an element in B and BC is an element in B and B is an ideal. Therefore, first it will be a subring. By using that, the property of subring, 1 minus BC plus BC will belong to B. And what is 1 minus BC plus BC? 1. So 1 belongs to B. We know that if R is a commutative ring with a unity, then any ideal in R which contains the unity will be the ring itself. That which means the whole ring R is the only ideal which contains the unity. So here it must be, B must be equal to R. So what we get? If there exists an ideal B which properly contains A, then it will be equal to R. So A is a maximal ideal in R. Next, we need to prove that if A is a maximal ideal in R, then what? Then R over A is a field. So we are assuming that A is a maximal ideal. A is a maximal ideal. To prove R over A is a field, we know that a commutative ring with a unity in which every non-zero element is a unit is called as field. So here we need to prove that each and every non-zero element b plus a in R over a is a unit. So in order to prove this element is a unit, we need to find the multiplicative inverse of b plus a. Okay, now consider the set B. The set B contains the set of all elements of the form BR plus A, where R belongs to R and A belongs to A. Here I am considering a set which is the set of all BR plus A such that R belongs to R and A belongs to A. Now we are going to prove that B is an ideal. And a subset of a ring is called as an ideal. First it must be a subring, then it must satisfy BR and RB belongs to B for all elements R in R and for any element B in B. So these are the things that we need to prove. Now by subring test we know that a subset is a subring if for any two elements A, B in B, A minus B also belongs to B. Then B will be a subring. Here the elements are in the form BR plus A. So I am considering two elements B1 and B2 where B1 is equal to BR1 plus A1 and B2 is equal to BR2 plus A2. These two are the elements in B and R1 and R2 belongs to R, A1 and A2 belongs to A. Now consider B1 minus B2 which is equal to BR1 plus A1 minus what? BR2 plus A2 and this is equal to B times R1 minus R2 plus A1 minus A2. Now look at this RHS. R1 minus R2 is an element in R and A1 minus A2 belongs to A. Since what? A1 and A2 are belongs to A, so their difference also belongs to A. Now the elements in this form will be where? Will be in B. Therefore, B1 minus B2 belongs to B. For any two elements B1 and B2 in B, the difference also belongs to B, which means what? B is a subring. B is a subring. Consider B dash in B and R dash in R. B dash belongs to B, therefore B dash will be in this form BR plus A. Now consider B dash R dash which is equal to what? BR plus A times R dash. And here it is equal to BR R dash plus AR dash. And here R and R dash are elements in R. Therefore this product will be in R. And A is an ideal. Therefore AR dash will be in A because A is in A and R dash in R. Therefore, by the property of an ideal, by the definition of ideal, AR dash belongs to R. So here this element belongs to R and this element belongs to A. So the element in this form will be where? In B. And here R is a commutative ring. So B dash R dash is equal to R dash B dash. So these two are in B. Therefore, B is an ideal. Therefore, B is an ideal. Hence, here look at B. B is an ideal and B contains A. B contains A. Here B is an ideal which contains what? A. Since A is maximal, here B must be equal to R. Otherwise, it will contradict the definition of maximal. Here A properly contained in B. Why? Because B can be written as B is equal to what? B times 1 plus 0. So this element is in B. B is an element in B and which is not in A. Therefore, A is properly contained in B and A is a maximal ideal. Therefore, B must be equal to R. Okay. Since B is equal to R and R contains unity, the unity can be written as what? Some B into some C plus A, where C belongs to R and A belongs to A. Now consider 1 plus A, which will be equal to what? BC plus A plus A. And A is an element in A, and here it can be written as BC plus A plus A, and here A is an element in A, therefore A plus A is 0, and here it will be equal to BC plus A, and it is equal to B plus A into C plus A. So here there exists an element C plus A in R over A such that B plus A into C plus A is equal to 1 plus A. Therefore, C plus A is the multiplicative inverse of B plus A, and B plus A will be a unit in R over A. And B plus A is an arbitrary element in R over A. Therefore, every non-zero element in R over A has a multiplicative inverse. So every non-zero element in R over A is a unit. Therefore, R over A is a field. Okay.